are some things that you need to know, and if you have heard it or you can Google it, you let me know what it means, yeah? This you have heard. I think this one I have mentioned. This one is our chapter. Can you read? Can you see it?
Yes, Prof.
Okay. What about this? What about this one? What else have you heard about morphism? Anything else you have heard about morphism? No. Homomorphism is this, right? F xy is fx fy, right?
Yeah.
One that I shared last time with
This
star or hash there, right?
X and this under operation before.
Yes, depend on the operation. Isomorphism is 1-to-1, onto, and homomorphism. Okay? What about automorphism? Automorphism is isomorphism from G to G. Okay, if you remember, our original isomorphism is from G to H, right? Where in this case, G and H are roots. Okay, so if we do F from G to G, then we call this automorphism. Okay, that is the difference. When G is equal to H, we can just say it as automorphism. So automorphism is an isomorphism when G is equal to H. So this is this when they are equal. Monomorphism, what does it mean? Now it's easy. You don't have to go to library. You can just Google. Can somebody quickly Google and read what does it mean? Or you can understand that. Anybody? Raise your hand. Did you get it? If you use your phone, you cannot Google, then it's hard. If you have a laptop for this and another phone, can somebody Google for a bit? Ain, what is monomorphism? Hannah, if you can just send a message to Hassan. Hassan is not here, right? Probably he thought that it's at 4. Or you can just screenshot, put our photo in the group. Yeah, Ain?
The Google say is an injective homomorphism. What's that?
Okay, anybody know what is injective? Injective means 1-to-1. Okay, so if it is a homomorphism, and then it is one-to-one, it is a monomorphism. It is not an isomorphism because it might not be onto. Okay, so these are the words that you have to know. Instead of one-to-one, there are another word which is injective. This is one-to-one. Surjective. This is onto. Plus homo. Okay? So these are just some terms that you have to know, especially isomorphism, automorphism, and homomorphism. But there are many others. If you look in Wikipedia, if you click on isomorphism, or you see so many other morphism. Okay, so just go through, at least you know the difference between all these terms. Okay, let's go through the examples on page, I'm not sure if it changed or not. This is the old one, the printed one is the old one, 63. Yeah, Hassan?
Assalamualaikum, Bu.
Waalaikumsalam. So you started at 4, we started at 3:45. Okay, so just sharing some terms regarding the morphism. Okay, instead of isomorphism, we do have so many morphism, isomorphism, automorphism, and so on. So I will erase this. We will go through the examples, okay? The first one, I will not go in detail, but I will just give some hints what you have to prove that it is an isomorphism. Okay, in this example, F is from Z to Z. So this is an automorphism because G is equal to H, okay? Sending an integer n to 2n. Okay? Now, in general, if you have this where Q is any integer, sending element to a multiple of the element, okay, this is an isomorphism. Okay, why? I'll just show just one example for the first one, and the rest you have to try. Okay, first one, F is 1-to-1, right? So suppose Fn is Fm, show n is m. Very easy, right? Very straightforward. If Fn is Fm, 2n is 2m, 2n is 2m, they are just integers, so n is m, all right? The second one is F is 1-2. So if you are given y in Z, okay, y will be 2k, right? Because Fn is 2n. So there exists k in Z such that f of, there exists, yeah, k. F of k is y. Okay. Is that okay or not? Is this okay or not? Is this okay? Why am I laughing?
Maybe 2y.
Maybe 2y?
Y, so
Okay. F of
equal
k is
to
2k, 2k is y.
okay.
What is wrong with this? Is there something wrong?
Not all images have pre-image.
Yeah. Actually, this is the wrong one, right? I assume y in z is 2k, but not all of them. Okay. 1 to 1, yes, right? 1 to 1, yes. Okay, because one will go to the other one. It will be easier if you look it this way. You have 0, -1, -2, or 1 and 2. This will go to 0. This will go to -2. This will go to -4. This will go to 2. This will go to 4. It's 1 to 1, but it's not on 2. Okay, because as Hassan said, there is a 1 here, right? All odd integers have no pre-image. Okay, this is wrong. This is wrong because I cannot assume y is 2k. If it's all 2z, it's okay. Okay, if it's 2z, it's okay. Now it's z. So this is an example where it's 1 to 1. Is it a homomorphism? Okay, it is. Okay, I will erase this. It's not on 2, yeah? This is to check whether it's homomorphism or not. So f of m plus n, is it equal to fm plus fn? Okay, because z using the plus, all right? So you take this side. Okay, this one is easy, right? It's straightforward. Right? This equal to 2m plus 2n. This equal to fm plus fn. Okay, this particular example, just want to show you that it's a homomorphism, right? Because the definition is on homomorphism. Okay. The same thing as number 3. Number 2 is similar addition, okay? But for this particular one, it is not an isomorphism because it is not onto. How do you show it is not onto? You can just say, taking 1 here, there is no x because it will be x over 2, right? X over 2 is not an integer, all right? So you just take one contrapositive, okay, for that particular one. So what you will write is, this is not onto, because if you take y in here, x will be y over 2, which is not necessarily integer. Whether you mention it in general or you mention it in specific. Take 1 in here, there is no x in here mapped to 1 because it's not integer. Okay, for number 3, there is a difference in the G and H, positive real number. Okay, so this is change. Okay, number 3, positive real number. Positive real number. An integer n an integer n is a to the n. Wait. Oh, sorry. Group of integers to the group of non-zero real numbers. I didn't see this. Okay, sorry. Question come later. group of integers addition to the group of non-zero real numbers. Non-zero real numbers. This is how you write non-zero real numbers. So this one is addition. You can put like this. You can also put like this, okay? Group of integers under addition to the group of non-zero real numbers under multiplication. Okay, so this is Fn to A to the n. What is A? A is positive real number. Okay. A can be any positive real number. I can put A as like square root 2. So f of 2 is square root 2 squared, something like this, right? Okay, so it's from integer to everyone. All right. Is it a homomorphism? Okay, is it a homomorphism?
Yes, yes, yes.
Yes, because the one gives the yes. So how do you show it? F of m plus n, is it equal to Fn times Fn? Okay, so what is f of m plus n is a to the m plus n, am, an, which is Fn, Fn. All right, so it is a homomorphism. Okay, next question, is it one-to-one? Yes or no? One-to-one?
Yes, 1-to-1.
Fm equals Fn. Is it m is n? A to the m is a to the n. A is just positive real number. You can take log, right? Natural log, both sides, right? So m ln a is n ln a. So you can divide because it's positive, right? So you have m is n. So it's one-to-one. What about onto? Is it onto? Is it onto? For all y in r minus 0, okay, do we have x in z such that fx is y? Okay, from here we can get fx will be a to the x is y, and x ln a is ln y. So from here we have x ln y over ln a. So given the y, can we find x mapped to y? And is this in z? Yes or no?
No.
No. Okay, it's not necessarily in z, right? Because Y, where's the Y? Y is real number. So this will be in real number, right? Okay. A, also positive real number. So you divide anything real number. Your X has to be from Z, right? So again, this is not onto. There will be something, this is quite hard to show. It's much easier if you can find one particular example or call it a counter example, right? This is to show in general, it's okay. But if you see, this is not master level, yeah? This is like primary school, secondary school, it's easy to see. Okay, your integer again, right? And this is your mapping. Okay, suppose my A, give easy one. A is, what do you want A? Give me a number.
1, 2, 3, positive.
Just one number.
1.
It's too easy. Maybe 2 just now, we have 2. 2 is okay, right?
2.
Okay, not too hard. Okay, what is the image of Z? But it cannot be 0 because nothing to the number can be 0, right? Okay, if you remember, if this is a number and it's integer, actually you can easily also see from the graph. But anyway, I will show here first. So this is the integer. If A is 2, right? This will be 2 to the 0. 2 to the 0. This is our n. N, and Fn is 2 to the n. This is 1. This is a half. You see, if you go to very negative, it will go closer to 0. And for this one, 4, right? Okay, or if you draw the graph, okay, then it will be like this, right? Because it's 2 to the power. If x is all negative, it goes closer to 0. Okay, go that way. This one is cannot be there. No, I mean for the y. Okay, because you won't reach 0. Okay, this one. That's why it close and close to 0. You can never reach for this one. Actually, this is actually bigger, right? It's actually this. If it's that, it's okay. No, it's not. Okay, you see, there is nothing. This is if R there. If not, you just get this, you can just get this. That's why 1, 4. And then here you get this, you get this. Only this. Okay, so one easy thing to show it is not onto is find some negative numbers, right? There is no x. Or find something in between, like 2. 2 is in here, but there is no such thing mapped to 2. Just now I show it's not in Z, right? So find x in Z such that fx is 2, right? So 2 in this case, 2 to the this one is 2, right? 2 to the 1. I don't want 2 then. I want 3. 3. Okay, 3. Okay, 2 to the x is 3. 3 here. What is x? X is ln 3 over ln 2, which is not in Z. Okay, so it's not really easy to see from here because it's integer, it's not continuous, but you can easily see from here. There are so many numbers in here which cannot have the prime image. Okay, so many of them, anything in between. If you go one more, 3, you get 8. So any numbers in between this, 5, 6, 7, there's no image mapped to that one. So if you get a question to show it's not onto, you can either show it in general, like just now, I just said natural log this over this is not Z. Or you can find one specific number from Y, which is not mapped by X. Okay. Now we move on to the next question. So number 1, just now it is not isomorphism because it is not onto. All right. Number 3, it is not isomorphism, it's just homomorphism. Okay, just now. All right. We move on. Okay. Theorem 5.1 is quite straightforward. The question is, given a homomorphism, then the image is a group. The image is a group. So you have to show it's close, it's associative, and the identity, and so on. Yeah, I'm not going to go into that. Okay, another one is if G is abelian, under isomorphism, H is also abelian. I mentioned this before. Okay, you look at the proof, theorem 5.2. Okay, you just using the homomorphism. If this part is abelian, it's a homomorphism, then the other part has to be abelian also. Okay, that is quite straightforward. Okay, let me just, it's quite interesting actually. Although it's straightforward, but how to write it out? Let G be an abelian group and F is a homomorphism. Then F of G is also abelian. This is another way to write theorem 5.2. The homomorphic image of an abelian group is abelian. Okay, so sometimes if you are given the theorem, it's not really easy to prove. You probably need to rewrite. Okay. So, okay. Now we have F is from G to H. All right. Or we can say this is a subgroup of this one, because it might not be everything, because we just know homomorphism. It might not be onto. So we just write this or just this. Actually, it's a, we want to show it is a also abelian. Okay. All right. So now the proof is let G be abelian. Then for all GH in G, GH is HG. Okay. To show FG is abelian, that is to show FG, FH is FH, FG. Okay, if you write out what do you have and what do you want to show, maybe it's easy, right? So we take this, and this is equal to this, since F is a homomorphism, right? It's a homomorphism. Okay. It's a homomorphism, so this is equal. But I want to show the fact that it's a billion. But FGH is FHG, which is equal to FHFG. Okay, so this is equal because it's a homomorphism. This is equal because a billion. Okay, from here to here is a homomorphism. So you can see that this is equal to this, which is this. Let me see this. I want to show this. Okay, and then what you have is this equal to this one. So this is equal to this one. Okay, so in the theorem, it's quite simple, but you have to use all the facts given in the theorem. Okay, the theorem gives you a billion, the theorem gives you homomorphism. Okay, next one. The homomorphic image of a cyclic group is cyclic. In the proof, the one dot 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 is supposed to be in the center, yeah? A dot A dot A. Hannah, can you just take a note of that one? I'm not sure if I changed there, but here. Okay. The homomorphic image of a cyclic group is cyclic. So if I change this cyclic, then this has to be also cyclic. Okay, meaning if two groups are isomorphic, they have to be both abelian, or they have to be both non-abelian, or they have to be both cyclic, or they have to be both not cyclic. Okay, if they are isomorphic, they have to have these properties. I am not saying if there are two groups which are cyclic, they're isomorphic. No, I'm just saying if they are isomorphic, they have to have the same property. Okay, if they want to be isomorphic, they have to have the same property. I'm not saying if two groups which are abelian have to be isomorphic. No. Okay, it's just one way. Understand? Okay, if G is isomorphic to H, G and H have to be both abelian, or both non-abelian, or both cyclic, or both not cyclic. All right, so this is one-way property. So the homomorphic image of a cyclic group is cyclic. How do we show this? Okay. So the same thing. Now, the different thing is, let G be a cyclic group generated by G. Okay? G until probably order for the n, okay? I just suppose cyclic growth for the n, so this is until n minus 1. Okay? Okay. Now, suppose I have, okay, so G is cyclic. This one is the homomorphic image of f of G, okay? You will have like E, G until G to the n minus 1. You will have also E here, okay? For this one, you have f of G until f of G n minus 1. All of those things, okay? Now, any x in here is in the form of some G, all right? Which is actually G, G until G. By homomorphism, this is G, 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 which is actually Fg to decay. Okay, what am I showing? I'm showing, suppose I have X in here. Suppose I have X in the image. Okay, it has to be some kind of power of G, the image of some element of power of G. So take anything X in here, it is the image of some power of G because it's cyclic. And G to the K is G times G times G. And since it's homomorphic, it's Fg times Fg until at the end, which is Fg to the K. What does it mean? It means that any X is a power of Fg. This is true for all X in here. So I can say that f of G is generated by f of G. So it is also cyclic. Okay. All right. Okay, I mentioned earlier that you map a subgroup to a subgroup. So if you have a theorem 5.4 says, okay, if f from G to G is a homomorphism, and H is a subgroup of G, then FH is a subgroup of the, oh, I use a different one, yeah. Okay, if F is a homomorphism from G to G star, H is a subgroup of G, then FH is a subgroup of G star. Okay, and the proof is quite straightforward. Let me draw. Okay, let me draw. How do you say about the proof? Okay, this is your G. This is your G star. This is your H, a subgroup of G. Since H is a subgroup of G, E of G is in H. Okay. Now, this will be the image of H. All right. So this is also the in the image, the identity of G star. Okay. Right. So f of E. So suppose this is f. So f of E is also in f of H. It has to be inside. Okay. Now, to show it's a subgroup, you take one image in here and the inverse. Okay, so fx, one step subgroup test, yeah? inverse inside. This is in G because it's a subgroup, right? H is a subgroup. So this is in H, so this is also in FH. Okay, one-step subgroup test. Okay, you can bring this outside and inside also by the homomorphism. Okay, last time I've shown about isomorphism. Okay, do I have time? Okay. Let's go to properties of isomorphism. Okay, before that, example 5.7, I ask you to go through and read your notes first, right, before class, okay? Go to example 5.7, decide whether phi is an isomorphism or not. Okay, so the first one is phi z plus 2 z plus with phi of n equal negative n. Before we do some calculation, let's do some thinking. Okay, you have to read one by one. You are given phi is integer, so it's a plus, to integer. So you're thinking of the whole positive, negative integers, right? Okay, mapping to also integers. Phi of n is negative n means the positive one you map to the negative one. The negative one you map to the positive one, right? What about 0?
0 back to 0.
0 is mapped to 0 because negative 0 is 0. So easily, you think about this, it's 1-to-1, right? It's onto, and you just check homomorphism. But homomorphism is quite straightforward. So when you do, phi is 1-to-1, quite straightforward. Phi n equals phi m, meaning negative n is negative m, which gives n is m. Phi onto, for all, call it y in z, find x in z, such that fx is y. So you put in fx is y, fx is y, so negative x is y, so x is negative y. So just take the negative, right? And it's also in z. Make sure you double check this is also in z. So given any y, what is the x? X is just the negative of the y. And the third one is homomorphism. So phi of n plus m, is it equal to phi n plus phi m? Is it equal? So you take phi of n plus m is negative n plus m, right? Okay, because this is quite straightforward. So this show, but you have to make sure they are inside Z, because earlier you see some of them, they are not real integers and so on. So this is an isomorphism. Okay. Okay? If it is okay, you can, if you don't want to unmute, you can show your thumbs up. Let me try. Okay. Okay. At least I'm not talking to myself. Okay. Now go to number 2. Think first. I'm not going to give you the answer. Think first. If you're ready to tell me something, probably someone can volunteer and give me the answer. The question is it an isomorphism? Number 2. Phi is from the general linear group, 2 by 2 matrices, entries of real numbers to real numbers. So you are mapping a matrix with determinant not 0. Okay, that's the definition, yeah? 2 by 2 matrix, entries real, determinant not 0, to real number. Okay, let me give an example. What is this equal to? Can somebody give me the answer? Vian, can you give me the answer?
Negative 30/2.
Okay,
Negative 30/2.
wait, Tan. Vian, do you remember how to find determinant of a 2 by 2 matrix?
Yes.
What is it?
A
AD minus
AG minus
BC.
BC.
Okay, this is the determinant. Okay, what is the determinant of this?
1 plus 1
You multiply
with 1
and then add.
and 2 multiply 3.
Okay, so the answer will be 1 times negative a half plus 2 times 3.
3.
5.5, right?
Right.
Right? This is right? So this is a real number or not? Yes, it's a real number.
So
So
minus
you have
minus,
to.
minus.
Minus, doctor.
Oh, okay.
13.
13, minus 13, minus 13.
13. Okay. You know, at school, the teacher will say this. I intentionally do this to see if my student is awake or sleeping. So Tan already gave the answer just now. Okay, so is this a real number? Yes, right? It's a real number. So that is why you are mapping a matrix to a real number. Okay, now my next question, is it 1-to-1? if I give you any real number, can you give me a matrix matched or mapped to that real number? Yes or no? Yes or no? Okay, is phi 1 to 1, right? Okay. No. I want to, my question is different than the, I was asking the onto, right? I don't want to do 1 to 1, it's too easy, that's why. Is phi onto. Ah, I skip 1 to 1, I'll tell you later. What do you think? Let me ask one by one. It's okay. The answer is very easy. It's either yes or no. Okay, don't tell me not sure. Yes or no. You can unmute, yeah? Ahmad, yes or no?
Yes.
Yes. Lava?
Yes, doctor.
Yes. Tan?
I don't know.
You don't know. Okay, yes or no, or I don't know. Hannah?
Yes.
Yes. Shihab?
No.
No. Imanina?
Yes.
Yes. Hassan?
I think no.
No. Ain?
I think no.
No. Vian?
Yes, I think yes.
Yes. Amtinan?
Yes.
Yes. Wali?
I think yes.
Yes. Okay, we have like 3 no, right? If I give you a number, say I can take any number, y. Y is in R, right? Can you give me a matrix that is mapped to Y? Of course. Right? If I give you a Y, in here, this is mapped to Y, right? But, there is a but. Why do you say it's not? For example, you give me a number 3, right? Now we are showing it's onto. We have to find a matrix mapped to 3. So I said, okay. Yes. From that, the determinant is 3, right? Okay, so give me any. But what is wrong? Is there anything wrong that you say is no?
0.
0.
Y equal to 0.
0? What about? Cannot be, right? Because you can never have a determinant because this is
0.
not equal to 0,
Yes.
right? The determinant not equal to 0. So you can never find this that it match to 0. So everything else is okay, except for 0 is not an image. This is the problem. Okay, anything else is okay. So this one is not, but you have to think a little bit. Okay, yes, you can find any number y match to it, but this is general linear group. Determinant cannot be 0, so there is no way you will find a matrix in which the determinant is 0. So 0 is not an image, so it's not onto because of 0. But if I change the question, this, okay, if I change this, yes, it is onto, okay, so I can change that. All right, I did already number 3 just now, okay. Now number 4 is very close to this one, okay, number 4. Number 4 is 2 by 2 matrices, 2 real number. 2 by 2 matrices under addition. That one earlier is under multiplication. That's why the determinant cannot be 0. Okay. Do you know what a trace is?
Sum all the diagonal.
The sum of the diagonal.
Hmm.
Yeah. If you have A, B, C, D, the trace is A plus D. Right? So if A is Aij, it has to be square matrix. Then the trace of A is the sum of the diagonal. Okay. So for example, trace of, in general, A, B, C, D is just A plus D. Okay, that is the trace. That's the sum of the diagonal. Okay. So the sum, the trace of a sum is the sum of a trace. It's very easy to show, right? You take A plus B, so it's A plus B, you can just separate, right? You add and then you trace of that. So it's homomorphism. Okay. Oh, just now, I forgot to mention, just now it is not even 1-to-1 because 2 matrices can have one determinant, same determinant, right? That's why it's not 1-to-1. Just now it's not 1-to-1. For example, determinant of 1, 2, 3, 0 is equal to, let me make it easy. 1 minus 0 is 1, right? Okay. The determinant here is 1. The determinant here is 1, but they are not equal. Right? So FA equal FB, but A is not B. So it's not 1-to-1. You can have 2 same image with 2 different. So if FA is FB, this is equal to 1, right? But A is not B. So in this case, it's not 1-to-1. 2 can go to 1 same 1. Okay. Also here, 2 different matrices can have the same trace, right? Okay. Try to write down 2 different matrices that have the same trace. Very, very easy. Just find 2 matrices with A plus D equal, right? So you can put B or C, you don't care. Maybe you put 1, 1 here, another one, 2, 0, right? So they can go to the same number, but they are not the same matrix. So not 1-to-1. Is it onto? Onto, the answer is yes. So I can ask you, why is it not an isomorphism? Okay, or I can ask you, show or decide whether each property of the isomorphism is satisfied or not. Meaning, even though it is not, but I want to see whether you understand each property. Okay, for this one, so yes, it is a homomorphism. No, it is not onto. No, sorry, no, it's not 1-to-1, but it is onto, right? So any number in R, like A in R, you can just do this, right? Map to this one. So it is onto. Okay, there is no exception. So in this case, although it is a homomorphism, it is onto, but it is not one-to-one. Hence, it is not an isomorphism. Okay, so you have to read my question very carefully. If my question said, decide whether this map is an isomorphism or not. Okay, then you just choose the one that is not. If the answer is not, you just choose the reason that it is not. You don't have to show all three. Okay, since it is not one-to-one, just show not one-to-one. So it is not an isomorphism. If it is, if there is another question, it is an isomorphism, you have to show all three. Okay, you have to show it's a homomorphism, it's one-to-one, and it's onto. But if I ask you, okay, to determine or to show or to check each property of isomorphism for this mapping. Okay, check each property of the isomorphism of this mapping. Then decide whether it is an isomorphism or not. That means I want to see whether you really understand each property, yes or no. So you have to check homomorphism, yes or no. You have to check one-to-one, yes or no. You have to check onto, yes or no. If the answer are all yes, yes, it is an isomorphism. If any of those answers, any one is no, no, it is not an isomorphism. Okay, is it clear? Where is your thumb? If it is not clear, just interrupt me, okay, and ask me to repeat if it is not clear. Otherwise, I will think that each of you is clear about this, okay? So go back to the last one, okay? So this is the last one for this class. I also mentioned about automorphism, okay? And last one will be the kernel, all right? Okay. Okay, last example. And I will go to the kernel, I will stop for today. Then there's some exercise that you can try. In next week, maybe I will give you what to do for the next assignment, but not this week, you can just try. The last one is number 5. Phi, f is continuous function, yeah? 2r star, which is r without 0 under multiplication. That's r star. And f, help me, Hannah, to put f is continuous function. Just so the next time I remember to note this. I don't know where my f continuous function, yeah. Okay, and phi of f is everyone knows this, right? You have passed your degree and calculus. This is integration, right, of fx dx from 0 to 1. Okay, can somebody tell me what this means? Actually, if you draw fx, what does it mean? What does it mean? Can somebody tell me? Or you forgot already, you take calculus. Yeah? What does it mean?
Area between 0 and 1.
The area underneath the curve with the x-axis, right? Between 0 and 1. Okay? This is the x-axis. This is fx. This is 0. F0, and this is 1, F1. So it's the area under the curve. That is the integration of fx in between 0 and 1. Now, is it an isomorphism? Okay, so you ask yourself, is it an isomorphism? Can we show that it's homomorphic? It's from f, all kind of function, continuous function, to a number. Because when we do this integration, we will get one number, which is the area under the curve, right? Or above the curve, the area between the curve and the x-axis. Even if you have this, so is that. So now, can you show this? Okay, by integration property, yes, right? Because phi of f plus g is equal to f plus g x dx. I haven't taught calculus for the longest time. I used to teach calculus last time. So, right? You can separate. So this is phi f plus phi g. Okay, so it is a homomorphism. Okay, now I want to ask you, is it 1-to-1?
No.
Why not? Why not? You can have two different functions with the same area, right?
Yes.
Ah, you can have, because if
Operation.
equal does not mean f is equal to g. But can you come up with one specific example? What if fx
S squared. S cube. S squared and S cube.
x squared and s cubed? Is it? This one we will have x cubed over 3. Okay, x cubed, you integrate, right? X cubed over 3 from 0 to 1. The answer is 1/3. If you have this, the answer is 1/4. They are not the same. Well, do you have something else? You can multiply something. Just find something with the same. This is fx equal 1.
Maybe 0 to no to half and half to 1.
What if you have something with x? 2x, right? I just use this because this is a box, right? Fx equal 1. So it's just 1 times 1. So the area is 1. For this one, it's x squared. 2x squared over 2 is just x squared from 0 to 1, right? So it's also 1. Okay. There are many other. There are a lot. Okay, so, find a triangle also. A triangle. Y equals x to x. Oh, I have this. Okay, anyway, this is not 1-to-1. Okay. But is it onto? Is it not onto? Right? Because you can also have a dot here. Okay, anyway, I'll stop here. But you just read through. Last one would be go through the rest. And definition 5.4 I have here is kernel of a homomorphism. So this is the last one in which kernel of a mapping phi is defined as whatever map to 0. Okay, so if you have phi from G to H, kernel is G in G, phi of G is 0 in H, or E, sorry. What is mapped to the identity? Okay, so the identity has to be inside the image, right? When you see that is equal to 0, the 0 there is the identity. Okay, I have to also change that to E actually. Please change the equal to 0 to the identity. So we want to do that.